All right. So from last time, I introduced the notion of the stopping time. Right. So recall what? So tau is a stopping time. So if the event, so the event tau is equal to n can be determined by the past up to xn. So x naught, x1 up to x7. Yeah. And the example that I mentioned were what? So ty is a stopping time. tky in general is a stopping time, or stopping time. In other words, if I give you the trajectory up to n, then you can tell me definitely that those events occur or not. All right. So the other one that I like to mention is that tau being the last time visiting little y. Okay. So we already have the first time, second time, third time, they are stopping times. But how about the last time though? What do you think? No, actually the last time is not a stopping time. So say t is equal to n, right? Suppose I tell you a trajectory, let's say following, let's say maybe just for the sake of illustration, maybe put number 3 maybe. All right, say 0, 1, 2, 3. Start somewhere here, jump. All right, so maybe hit right here, maybe, and then go up. Right. Suppose I give you that trajectory. Can you tell me? So I guess I don't really want to do that. Maybe I want to go or stay at y. I want to stay at y. All right. So can you give me the definite answer whether that event tau equal to 3 occurs or not? In other words, the last time I visit little y is 3. No, we cannot, right? Because we don't know what happens in the future, right? So in order to know the last time is 3, that means I need to make sure the rest here will never visit 1, right? In other words, I need to know the future, not only up to step number 3 here. Okay, yeah, does that make sense? Okay. So we do not know. Okay, so we do not know definitely whether this event tau is equal to 3 occurs or not. So we need to know the future in this situation. All right. And so what is the point of the stopping time? Basically, in the theory of the Markov chain, basically the idea of the stopping time is the following. So let me give heuristic, say explanation for the stopping time. And then I will discuss the theorem later on. So let's say I start from time 0. Okay. So let's say I start right here from time 0. I could go anywhere, right? So the distribution of the next step is totally determined by the transition matrix, right? This is the same thing as, suppose, let's say little x right here. Suppose instead of starting from time 0, let me start from time number 3. I forget about whatever happened before in the past. All right. And as you can see, the distribution of the chain starting from step number 3 exactly the same as the distribution of the chain starting from step 0. Okay, that is the property of the Markov chain. The thing is, the number 3 here is a deterministic time. This is a deterministic time, right? So how about what if I start from a random time? And so the theory says, suppose I have a tau here, suppose tau is a stopping time, all right, which is random. This is totally random. Then the theory says, if I start at x at time random time tau, then the distributions of the chain is exactly the same thing as starting from time 0 or starting from time 3, basically. All right. So say distribution of the chain xn starting from the random time, as you say, random time tau is the same, basically the same as, say, the distribution of the xn starting from time 0. All right. It turns out that is one of the key property of the stopping time. All right. So you just, like I just flow the chain forward up until the stopping time, then I'm going to stop. Think about it. I'm going to stop the chain right there, stop for the moment, and then starting from there, I flow it forward. Then the distribution starting from that random time is exactly the same as if I start from time 0 or any deterministic time. Okay, which is really, I would say, really amazing. However, the theory is not really that complicated. And to illustrate this, all these wording explanations, let me mention the first. I believe this is lemma number 1, so-called strong Markov property. Okay. So let's say given a stopping time tau, stopping time tau, all right, then the probability of x tau plus 1 is equal to a little z, right? Given x tau is a little y and tau is equal to n. This probability is exactly the same as the little pyc. So suppose I start the chain from the stopping time tau, right there at the little y. Then the chains, I will end up at z in the next step. Exactly the same thing as I start from time 0 at y, go to z in step number 1, basically. Same thing. Okay. All right. there any question so far? So how we do this? So let's just say just a sketch, I guess. Let me just prove it. So let me start with just the definition of a conditional probability. I have probability of x tau plus 1 is equal to z, given x tau being y, and tau is equal to little n. That is the same thing as x tau plus 1 is equal to z, together with x tau being little y and tau is little n. Everything divided by this event. All right. So then, what do we need to use now? So now we know since tau is a stopping time, right? Tau b and n can be determined. So let's say tau, so x tau is equal to y, tau b and n. This event can be determined by the past, can be determined by so the sequence from x naught to x. In other words, I could write the following. So let me consider all the trajectory. So trajectory. So let's say so let's say this is I have xn is equal to y, and xn minus 1 is a little xn minus 1. Other way back to x naught is a little x naught. All right. So I should say consider the collection. Consider collection. Let me denote that to be V of all trajectory. Just that whenever such a trajectory occurs, then I have this event occurs. Okay. Just that when that say x is equal to little y, x naught is little x naught occurs, then the event x tau being little y and tau is equal to n occurs. Basically, I am looking at all the extinct trajectories of that up to time n here, right? I visit little y, and in the middle, I could go anywhere else. Right, so let's say it's not here, maybe, you know. Other ways of that at the time n, I visit y, and this is n here. So tau is equal to n, and x tau is little y. Okay. Yeah. So let me consider those collection, the collection of such trajectories. All right. Then what I can do is I can decompose the first what? Sorry, I should say the numerator. Then I would say I have what? Probability of x tau plus 1 is equal to z, x tau is equal to little y, and tau is equal to n. This event can be decomposed into the summation such path V, right? just have the x tau plus 1 is equal to z, and I have xn is equal to what? This is to little y. Xn minus 1 is equal to little xn minus 1, all the way down to x naught. All right. So I should mention this is tau is equal to for the sake of safety. All right. All right. Yeah. So I can just decompose. How can I do that? That's because that is just can I do that? Can I really do that? Can I just decompose the original event into that sum? Yeah. And so, you know, like I have what? So I have suppose I have an event, say B, right? Can be decomposed into the following. So BK, where BK or disjoint. Then the probability of A intersecting B, right, can be decomposed into just the summation of the probability of A and BK, right? Yeah. Yeah. So I should have mentioned, maybe for the sake of completeness, I should have mentioned. So in other words here, maybe for this. In other words, the event x tau is equal to n, tau is equal to, sorry, little y here, tau is equal to n. It's just the union of such path in the V. So I have starting from xn is equal to y, x naught is little x, right? Yes, that should be clear now, I guess. Yeah. And so now I'm gonna just well, because I already know tau is equal to n, so tau plus 1 is just n plus 1, basically. So now keep going with this series. Summation such paths in V, right? So this is the same thing as I'm going to replace the tau by n plus 1, right? Is equal to z. Xn is to the y. Xn minus 1 is xn minus 1 the way down. X naught, right? Then I will just use the conditional probability up to this point, so that I can invoke the Markov property. Right? So I guess summation that probability of xn plus 1 is equal to z given xn is y, whatever in the past here, and then multiply by, of course, xn is equal to y, xn minus 1 in little x minus 1, all the way down to x naught. Right. Yeah. And then by the Markov property, this conditional probability is just little p starting from y and go to z one step. So then I can pull that out. I can pull that out, right? So I can pull that guy out of the sum. I have little p, y, z. Inside of the sum I have, so such are the paths in the capital V. Probability of xn is equal to y. Xn minus 1 is xn minus 1. X naught is equal to x naught. All right. And finally, that sum again is simply just this event, the probability of this event, because I already have this event can be decomposed into such paths in the collection V. And so because they already joined, right? They already joined, and so there's some a probability that is just probability of the event x tau being little y, and tau is exactly it. Right. And so what do I have? So after a while working through the math here, I have the numerator is just the little pyz multiplied by that probability. And that probability is just the denominator. So we'll be canceling. So they will be canceling one another, giving me just pyz. So now turning back here, so back here, right? We have that, this, and then according to, so I have p little yz, multiply probability of tau b and y, tau b and n, divided by probability of x tau b and y and tau. And I am left with just pyz. Yeah. Is there any question? And as a consequence of this lemma, we have the following theorem, where we just delete the tau b and n inside of the probability. As a consequence, we have the following theorem. Should I have theorem number 2? Suppose tau is a stopping time such that the probability of tau be infinite is equal to 1, right? Then probability of x tau plus 1 being z given x tau being little y, this is exactly the same as pyz. Okay, so I don't have the event tau b and n here for the sake of safety, because now I know it has to be tau is being finite for sure. And so I can just condition on this x tau b and y. All right. Okay. Yes, please. Is this a Markov chain? Yeah, xn is a Markov chain for sure. Of course. And so this basically confirms the heuristic graph that I have from the beginning. If I run the chain up to a stopping time, stop there, and then start from there, then the distribution is exactly the same as I start from time 0, basically. Even though the time there is random, even though time there is random. Okay. For the proof of this, I guess just allow me to refer to the textbook to save time. But from now on, whenever you see a stopping time, I condition on it, then the future is the same as a deterministic chain. And so to give a maybe just a application of this strong Markov property. Oh yeah, so that's why they call it strong Markov property, right? So the Markov property is the one for the deterministic time step, but the strong Markov is the one for the random time step. Okay. So so maybe let me mention here. So the C textbook for the C textbook. Right. In the session 1.3. So to see an application, let me mention the next lemma number 3. So recalling the k time I visit little y. All right. So I have probability starting from y, the k time visiting y. Suppose that k time is finite, so that probability is exactly the same as the little rho y raised to the power k. All right, where the little rho little y is a probability that starting from y and I return to y finite time. Okay. This can be seen pretty intuitively, even though the lemma may be a little bit complicated, but it can be seen pretty intuitively. Just drawing the graph here, so I have y here, right? Okay, and I'm going to start from the time 0, say, start from time 0 here at y, right? Then I'm going to run the chain, say, up to here. So this is the first time I visit y. So this is my what? This is t little y, right? First time I visit the little y, and this happens with this probability, right? This occurs with probability rho little yy, probability rho little yy, right? And now, according to the strong Markov property, starting from that random time ty, I have a new chain, which is exactly the same as I start from 0 at y, basically. And so now start from here, keep going forward. Sorry, so let's say here, right? So then I end up at y again. So this is this will be my t little y square. So you can imagine forgetting whatever happened before in the past up to ty, starting from here, going forward. I have exactly the same chain. And so this will occur the same with the probability rho yy, right? In other words, I start from y. The first time I hit y again, that is rho yy. And so altogether, I have a double, basically. So that means I have to square up the rho yy for the ty squared. And similarly, say all the way, say t3y, the same thing. So start from here, I have a new chain, exactly the same probability, transition probability. And this will be rho yy, right? And so on, keep going, just keep going, all right? Keep going there. All right. So I guess let me give a sketch here of the argument. So I guess we can do by induction. By induction on the k. Right? So when k is equal to 1, that is trivial, right? Because well, that is just exactly rho yy itself. Like what the y, ty finite. This is just by the definition of rho yy. So there is nothing really interesting here for the k being 1, right? And then I'm going to suppose maybe like this, and suppose the formula. I believe that is the formula 1.4 in the book. Let me double check if I have the right labeling in the book. Yes. Okay. I suppose the formula holds for k. Right. I'm going to need to evaluate k plus 1. And now consider k plus 1. But here I'm assuming everybody knows induction. Yeah. Okay. Right. So what do we have? So I have property of little y, ty, k plus 1 being finite. Right. It's the same thing as probability of I start the chain from little y and evaluate this event, ty k plus 1 being finite. Just the definition of that event. Then, as usual, I will just get rid of the conditional probability. Ty k plus 1 being finite together with, so maybe just let me write here, so give me some space, divided by x naught being little y. Right, so I just got rid of the conditional probability. All right, so now what is the next thing I should do? So if I can visit y in k plus 1 times. That means I already visit y at the k time, right? If the k plus 1 times occurs, that means the k time has to occur, right? So that is the same thing as, just include it, t, k, y, finite, right? Yeah. And then, so now, how do I decompose this? Well, that is the same thing as, maybe, let me write over here. So, well, what the event t, k, y being finite is the same thing as the decomposition of the sum k starting from 1. Oh, sorry, maybe use another. N being 1 to infinity. Probability of tk plus 1y being finite, and tky is equal to n. It's not really 1. Of course, I have the denominator. Right? Can simply decompose the tyk being finite into these disjoint events. Yeah, so that would be just the series of that. So now we just had to condition on the tyk being n, basically. And because of the Strohm-Markov property starting from there, I have a new chain. And well, so maybe just say not bad by the Strohm-Markov property. Strohm-Markov property. We have the probability of tyk plus 1 being finite, tyk being n, x naught is y. This is the same thing as tyk plus 1 being finite, tyk being n, x what evaluated at that time, right? Tyk being little y, x naught is y. Yeah. And so it is conditioned on, so condition on this, multiply by the rest. K and then K. So now up to this point, basically I have exactly, so this right here. So to say this right here is the same thing as I start from y, and the first time I go back to y, basically, be infinite. Right. Because whatever happened in the past is irrelevant. I only start from here, this random time, at little y. Then this means the same thing as the first time I visit y, starting from this random time. Right? Whatever in the past is irrelevant. So this is the same thing as this, which is of course rho y according to my definition. I guess maybe for the sake of safety, let me sketch again. Yeah, looking the graph may be better. So 0 here, tyk, right? At this random time b and n, I have to visit y. And then starting from here, I have a new chain, the same distribution. So this will be tyk plus 1. Hit y again. So whatever happened before that is irrelevant. I don't care. I will just start the chain from this little y going forward. This is basically the first time I visit y, basically. All right. Here, I'm being a little bit, I would say, being a shortcut here. I mean, technically, you really have to write down everything in order to prove this rigorously. This is equal to that, but just leave that as an aside. Okay. But technically, I should have written more in order to explain the math here. But heuristically, it should be true. Heuristically, it should be true. Okay. All right. And so, well, so now just to pull it out, So I have P and what I have. So what do I have? So I have that sum. Right. So I have the series probability of x naught b and y. That is the same thing as the row yy being pulled out. Sum at the top, which is this. So probability of t, y, k, b, and n. X n is y. What else? X naught is little y, right? Divided by probability of x naught is little y. And so again, so this is just each of these events, they are the joint. So that back again can be simplified into this is the same thing as probability of t, y, k, b infinite. X naught is y above x naught being y. Right? Yeah. And well, so you can see immediately this guy right here will be just probability of t, y, k finite condition on I start from y, right? Basically, and according to my induction hypothesis, that quantity is rho yy raised to the power k. So this is equal to you can just say rho yy here multiplied with rho yy raised to the power k, and altogether I end up with rho yy. Right? Yeah. Shouldn't be too difficult up to this step. I guess just any question about this? Yeah. Okay. So maybe I don't have enough time to move on to the next portion. Let me come down. So this is just for the sake of safety. So some of you may be confused with the x evaluated at the time tau. So xn, x1, x2, x3, they are clear. They're just random variables. But how do I understand the x tau? Right? A bit confusing here. I have like a double randomness. So maybe let me give. So let me recall back here when back in the kindergarten you learned what is a random variable. If I ask you what is a random variable? How do you define a random variable? 10 years ago, how did you learn that? Yes. Exactly, right? So a random variable is just a fancy name for a function. So is a function from the probability space denoted by omega, targeting the my state space S, right? S here could be real values or could be, you know, state space. In other words, given a little omega, I have a map from little omega to X evaluated at omega, right? Which is a value in S, right? I'm pretty sure you have seen this. I'm pretty sure you have seen this before. And so basically, to evaluate the X tau is exactly the same thing. Exactly the same thing. So I have, you know, so here for each a deterministic time n, xn is just a function, say omega to s for each little omega inside this probability space. I have an xn evaluated at omega, which is an element in s, right? It's just random variable, nothing really fancy here. So now the same thing for the tau. Similarly, tau, a random time, right? So is defined technically as, now from probability space omega, I'm going to map to natural number union with the infinity, right? And for each little omega, I map to tau omega. Yeah, it's just the definition of tau, basically. A random time on the natural numbers. And so that you can think about the X tau now, it's just a double map, or I don't know. So now X tau, all right, X tau now is basically given by, so how do you define this map, X tau? For each omega, right? So for each omega, X tau omega is basically this quantity here is basically equal to the first thing I'm going to evaluate omega at the tau, right? That will give me a number, and then I'm going to evaluate the whole thing at omega, if that makes sense. It's just that. Yeah. Evaluate omega at the function tau. Plug it in here. Will give me the index of the time, right? And then for that index of time, evaluate omega for that x, basically given according to this rule. Okay, so that is how you understand the x tau mathematically. Okay, rigorously, that is how you define the x tau. Okay. All right, guys. I'll see you on Friday.